Good day, class, and welcome to our second lesson on organic chemistry. Like we treated last class, we started with hydrocarbons. And if you can recall, I said hydrocarbons are compounds containing carbon and hydrogen only. We went further to see the two types of hydrocarbons, that is, aliphatic hydrocarbons, which are straight-chain hydrocarbons without ring structures. We said aliphatic hydrocarbons are alkanes, and alkynes. Also, we looked at aromatic hydrocarbons, and we said aromatic hydrocarbons are also known as arenes. And these hydrocarbons are hydrocarbons in which the carbon atoms are arranged in a ring structure. For example, benzene, often called the benzene ring. We went further to see the sources of alkanes. How we could obtain alkane from the laboratory. And we said we could obtain alkanes from the laboratory from halogenoalkanes, that is reduction of halogenoalkanes, and also from hydrogenation of alkenes. Today, we'll be looking at the physical properties of alkanes. Descending the series, that is from methane downwards, their melting and boiling point increases with increasing relative molecular masses due to increase in van der Waals forces down the series. What we mean here is this. We said descending down the series, their melting and boiling point increases as their molar masses increases, meaning that the melting and boiling point of methane will be lower than the melting and boiling point of ethane. Ethane will be lower than that of propane. Propane will be lower than that of butane, and so on and so forth. As the series is descended, alkanes change from gases to liquids and then solids, which means as the series is descended, there is a change in state from gases, then to liquids, and then to solids. The first four members, that is from carbon 1 to carbon 4, that is from methane to butane, are gases. For example, the methane gas. The methane gas is a normal cooking gas at home. The gas your parents use in cooking is methane. From carbon 5 to carbon 15 are liquids, and carbon 15 and above are solids. This change in state from gases to liquids and then to solids is due to increase in van der Waals forces as the series is descended. The gases and liquids are all colorless with variation in their melting and boiling points. Due to increasing van der Waals forces down the series, volatility among the liquids increases as the series is descended. Because alkanes are non-polar, they tend to be insoluble in water and other polar solvents, but they readily dissolve in organic or non-polar solvents, such as kerosene, petroleum, diesel. As the series is descended, the melting and boiling points increases with increasing relative molecular mass. Relative molecular mass is abbreviated RMM. This increasing relative molecular mass brings about an increase in van der Waals forces. Holding the molecules together, hence increasing melting and boiling points. Among isomeric alkanes, that is among the isomers, the most branched isomer has the least melting and boiling point. This is so because the most branched has the least surface area and is the most spherical among the isomers. The consequence is that less energy is required to melt or boil it, hence the lowest boiling and melting points. Hence the lowest boiling and melting point of the isomer of the most branched isomer. The alkanes change from gases, that is carbon 1 to carbon 4, then to liquids, carbon 5 to carbon 15, like I earlier said, and then to solids, carbon 15 and above. This change in state is due to increasing van der Waals forces and increasing molar masses. The first 4 alkanes are colorless gases, and the liquids are also colorless. They are all colorless gases and liquids, with variation in their melting and boiling points. As the series is descending among the liquids, viscosity or volatility increases due to increase in van der Waals forces. They are insoluble in water, that is, alkanes are insoluble in water because they are non-polar but readily dissolve in organic or non-polar solvents such as diesel, petroleum, and kerosene. When we talk of water being polar, it means it has a dipole moment. Like you see from below, this is what we call a dipole moment. This water is being hydrolyzed as this. Water has this. But when we look at alkanes, we realize that alkanes do not have a dipole moment. They do not have electrical charge centers. Like you can see, let's take for example, methane. Methane has no dipole moment. Even if a hydrogen atom is being given off to form this, it has no dipole moment. Like we've seen, the next thing we're going to look at, next subheading there, is reactions of alkanes. Alkanes undergo mainly combustion and substitution reactions because the carbon to hydrogen and carbon to carbon bonds are purely covalent. Like I earlier said, alkanes have no electrical charge centers and they have no dipole moments, which means the bonds between the carbon and the hydrogen and the carbon to the carbon are purely covalent. Substitution reaction is defined as the replacement of one or more atoms. That is the replacement of one or more atoms by an atom or group of atoms. In this case, substitution is the replacement of one or more of hydrogen atoms by an atom or group of atoms. Like I earlier said, alkanes do not react with polar compounds like acids, alkalis, and dehydrating agents because alkanes do not have electrical charge centers to react with species such as permanganate. To have species such as permanganate, this is how you look at this is the structure of your permanganate. MnO 4 minus. It doesn't have. This is a charge, meaning permanganate has a dipole moment, has an electrical charge center. Also, alkanes cannot react with hydrogen ion. Alkanes lack this, they lack the electrical charge centers. Alkanes do not react with hydroxide ion because they lack electrical charge centers. Also, we'll see that alkanes undergo what kind of reaction? we said combustion and substitution. And I've defined substitution reaction as the replacement of one or more hydrogen atoms by an atom or group of atoms. Combustion reaction. What is combustion reaction? Combustion reaction is burning in oxygen. How do they react with oxygen? They undergo mainly substitution and combustion reactions due to the fact that the carbon to hydrogen and carbon to carbon bonds are purely covalent. The alkanes are nonpolar. The alkanes are nonpolar compounds. They do not react with polar compounds or polar solvents such as alkalis, acids, and dehydrating agents, because they do not have electrical charge centers to react with species like hydrogen ion, hydroxide ion, and permanganate ion. Even in their reactions with non-polar compounds, energy is required. Energy is always required in the reactions to initiate the reaction. 1. Reaction with halogens. Reaction with halogens is a substitution reaction. Alkanes react with halogens in the presence of ultraviolet light or at a temperature of 250 degrees Celsius to 400 degrees Celsius, producing a mixture of products. This is a substitution reaction, and the reaction mechanism here is free radical mechanism, which is divided into 3 steps. They react with halogens in the presence of ultraviolet light or at a temperature of 250 to 400 degrees Celsius, yielding a mixture of products. The reaction is free radical mechanism and is divided into 3 stages. The first stage is initiation stage. The second is propagation stage, and the third is termination stage. Let's look at an example. The example we're going to take is halogenation of methane. And remember, halogenation takes place in the presence of ultraviolet light, in the presence of UV light. The first stage is initiation stage. At the initiation stage, free radicals are being produced. Like you can see from below there, chlorine in the presence of ultraviolet light gives you chlorine free radical. The next stage there is propagation. The propagation stage, free radicals are being produced. And also, at this propagation stage, as the free radicals are being produced, other molecules react with the free radicals to produce more free radicals. Let's look at the example there. We have methane plus chlorine free radical is going to give us methane plus chlorine free radical is going to give us form another free radical, which is methyl free radical plus hydrogen chloride. Methyl free radical plus chlorine molecule is going to give us chloromethane plus chlorine free radicals. Like you can see from there, more free radicals are being consumed, free radicals are being produced, free radicals get consumed, they react with other molecules which are non-free radicals to produce more free radicals. The next stage there is termination stage. At the termination stage, no more free radicals are being produced. All the free radicals produced at the initiation and propagation stage are now being consumed. They are now reacting together to form a mixture of products. When we talk of a mixture of products, like the example we're using halogenation of methane. Mixture of products, we're going to find out that we're going to produce chloromethane or halogenated methane, and we're also going to produce ethane. You can see from the example there, methyl free radical reacting with chlorine-free radical to give us chloromethane. Chlorine-free radical reacting with another chlorine-free radical is going to give us chlorine atom. Now, we look at the third example there. It's going to have a methyl-free radical reacting with another methyl-free radical to give us ethane. The next reaction we are going to look at there is combustion reaction. Like I earlier said, combustion reaction is reaction with oxygen. They burn in air. Alkanes burn or react with excess oxygen or air to yield carbon dioxide and water. You can see from the example there, methane plus excess oxygen gives us carbon dioxide gas plus water gas. Now, the subheading we're going to look at is cycloalkanes. Like I earlier said, our next subheading we're going to look at is cycloalkanes. Cycloalkanes are saturated hydrocarbons where the carbon atoms, that is the saturated alkanes. Cycloalkanes are saturated hydrocarbons. Hydrocarbons where the carbon atoms are arranged to form rings. They have higher boiling points and are slightly denser than their corresponding alkanes. I'll repeat. We say cycloalkanes have higher boiling points and are slightly denser than their corresponding alkanes. When we talk of their corresponding alkanes, we mean cyclopropane has a higher boiling point and density than propane. Butane is compared with cyclobutane. Cyclopentane will be compared with pentane. You can see from the example below there, we have the structures, some structures of cycloalkanes. We have cyclopropane as the first. The second there is cyclobutane. The third is cyclopentane. The fourth, cyclohexane. Reactions of cycloalkanes. Cycloalkanes undergo addition reactions. And when they undergo these addition reactions, they yield corresponding alkanes. They yield their corresponding alkanes or alkyl compounds. They undergo addition of hydrogen halides, that is, and addition of the reaction with water to form alcohols. When they react with hydrogen halide, they form halogenoalkanes. When they react with hydrogen, they form their corresponding alkanes. The first reaction there is hydrogenation. That is addition of hydrogen. You see, cyclopropane reacting with hydrogen in the presence of nickel catalyst at 140 degrees Celsius is going to give us propane. The next reaction there is addition of hydrogen halides. You see the example there, cyclobutane reacting with hydrogen chloride is going to give us chlorobutane. The next reaction there is going to be reaction with water is going to give us alcohol. For example, we have cyclopropane there reacting with water to give us propanol. And here we've come to the end of our lesson for today. In our next class, we're going to be looking at alkenes. Alkenes are the second class of aliphatic hydrocarbons. Thank you and see you next class.